Neither snow, nor rain, nor heat could have been accurately predicted 200 years ago because the idea of figuring out what the weather would do next was considered absurd. The gloom of night, however, was reliably anticipated. I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. On Big Picture Science, we step back to get the wide-angle view on science and technology, and in this episode, the weather is one of our few shared experiences. Talking about it is a reliable icebreaker, and we're more often than not complaining. But we're actually really pretty good at predicting the weather, although there's room for improvement, and we're not very good at modifying it, although we've tried. And yet we haven't given up attempting to seize control of the rains that produce the rains. Well, what does this persistence mean for a future when we might consider a techno fix to climate change? It's Weather Vane.
It's tempting to think that you could do better than the local TV weather guy. I mean, you have an outdoor thermometer, a barometer, a weather vane, even a rain gauge. What else do you need to declare that it'll rain tomorrow?
Weather forecasting is a much more involved technology, and it involves getting observations over the entire planet and using supercomputers to integrate equations. So it's probably the most complex thing our species does scientifically and technologically.
Sure, we can complain about the weather, grumble about the rain when the forecast called for sunshine, but thanks to sophisticated orbiting instruments, weather forecasts are much more accurate than they were just 20 years ago.
Satellites are our eyes in the sky, but as good as they are, when it comes to predicting the behavior of large storms, such as hurricanes, they can disappoint, says Cliff Mass, an atmospheric scientist at the University of Washington.
He says the U.S. is falling behind in weather forecasting, but could improve by adopting something called Ensemble Forecasting. The idea here is that you take a number of scenarios and you average the result. But for that, you need complex modeling software to produce the scenarios, which we don't have.
Well, the key to forecasting is having comprehensive global information. And right now, weather satellites are the main source of that information. 95 to 97% of all the observations we use for weather forecasting comes from satellites over all the oceans, over the entire atmosphere.
But can the satellites actually see down into the clouds? I mean, they're just looking at the cloud tops, aren't they?
No, some of the satellites can actually look down into the clouds. They can see temperature and humidity and other features three-dimensionally. It depends on which wavelength we use. It's sort of like Star Trek, except we can do it better than Star Trek.
In what sense? There's not much weather in space.
No, but on Star Trek, when they orbited a new planet, Spock would always do the scan of the planet, and it would be this wonderful structural information they'd have on there, and they would tell us a Class M planet, and this atmosphere was like this, and they could see the storms and things like that. We can do better than that. We have a large number of weather satellites up there that are giving us information about the detailed structure of the atmosphere. It's telling us also where the clouds are, what the temperature of the clouds are, the temperature of the surface. It's even telling us the waves and the winds near the surface over the ocean. So we have amazing technology for determining what the atmosphere and the ocean surface is like.
Well, you're painting a pretty attractive picture here, Cliff, and yet, we still get it wrong. Certainly, if you make a forecast for 2 weeks into the future, I usually assume that's not terribly reliable. The whole thing about forecasting is that weather, of course, is a very complex system and chaotic in some sense. So even a small, largely unpredictable change, variation, can have large-scale consequences just a few days down the line. Is that not so? I mean, is it really a chaotic system?
It is a chaotic system. A chaotic system is one in which small differences in the initial state can eventually produce large differences in the forecast. Atmosphere is certainly like that. But because of the satellites, because of the other observational assets, we have a much better description of what's happening. And our computer models now have become extremely sophisticated. You go back 20 years ago when we virtually got every one of the storms wrong. When they would come, and the next day the forecast was bad. And now we're pretty good. We don't have any more surprises, and virtually every storm is predicted the day or the few days before.
Well, can you describe the atmospheric and even oceanic forces that come together to form a hurricane, and why are these storms so violent? Where does the energy for these storms come from?
Well, hurricanes derive their energy from moisture, and that moisture originally comes from water evaporated off the tropical oceans. So that's where the energy from hurricanes comes from. It's water vapor. That's different than mid-latitude storms that hit here up in Seattle. Our storms get their energy from the differences in temperature between the north and south latitudes.
Can you give us an example of how a hurricane forecast was bungled to illustrate what's lacking in our weather forecasting?
Hurricanes, it's a mixed situation. Our ability to forecast the track of hurricanes has become immensely better. We're very good in describing and forecasting where hurricanes will go during the next few days. On the other hand, our ability to forecast the intensity of hurricanes is not good and has not improved substantially. A great example of that would be Hurricane Matthew, which hit Haiti, and it went from a Category 1 to a Category 5 storm in one day, and basically we didn't forecast that. So track, we're great, but intensity, we're not.
You've been somewhat critical, in fact, of our ability to forecast the weather. You would think that the United States would lead the world in this capability. Doesn't seem to be the case.
That's right. So, my point is we've come a long way in weather forecasting globally. We're not the only ones. The United States is not the only one doing forecasting. But the problem is that the United States has fallen behind some of the leaders, like the European Center for Medium Range Weather Forecasting or the UK Met Office. We're no longer the leaders in global weather prediction, and we're not doing what we should for regional or local weather forecasting.
In which ways have we fallen behind? Which significant ways, Cliff? I mean, is it just equipment? If we buy some more computers, maybe invest in somebody else's software, or is it just, the total effort being given to the problem, lack of funding, lack of organization? Where's the problem?
Well, the big problem is probably our models. Our models are inferior to those used elsewhere. That's the code that describes the physics of the atmosphere. It's the code that describes how we combine the observations to describe what the atmosphere is like right now. These are complex numerical models that are run by weather forecasting centers. These are models that encompass millions of lines of code that include everything from combining the observations to describe the state of the atmosphere, to describing how clouds work, how the boundary layer works, and the drag in the boundary layer. All these physical processes are described in code.
You've advocated for something called ensemble forecasting, in which I gather you generate numerous examples of possible scenarios. Maybe you could explain that a little bit and why it would be better.
Well, the future of forecasting is definitely in what we call probabilistic prediction. We can't run a model once and say, here's the forecast, because there's definite uncertainties in that forecast, uncertainties in the initial state and uncertainties in the physics. There's a much better way to forecast. This is called ensemble forecasting. And that is, instead of forecasting once, run the model once, run the model 50 times. Each time starting slightly differently in terms of the initial state, each time using slightly different physics. And what we get then is a whole collection of forecasts. And we can use that to figure out what the uncertainty of the forecast is, and we can actually calculate probabilities. For instance, if you have 50 forecasts and half say rain and half say no rain, well, maybe the probability is 50% for rain. But you can do this with temperature and wind, humidity, anything. So we need to use ensembles to go probabilistic in our forecasts.
So this preference for ensemble forecasting, I can understand that. You run the model many, many times and you look at what comes out. Are we only running the model once now? I mean, is that the situation?
Well, right now we are running some ensembles, but they're too low resolution and not enough of them. That's true on the global side. We are not running a high resolution ensemble over the United States at enough resolution to get the local features and thunderstorms and convection that we need to do. So on the global scale, we're doing a poor job at it. On the local scale, we're not doing it at all.
What do you think that these improved modeling techniques will do for forecasting phenomena such as snowstorms or tornadoes? I mean, tornadoes are pretty local.
Right, we have to differentiate between the large-scale type of weather features like snowstorms and things like thunderstorms or convection. Um, I'm very optimistic that we can get more forecast skill by using these ensembles, higher resolution, better models, better data assimilation, how we use the observations. I think we can push the horizon of forecast skill for the larger scale phenomena out, several more days. So I think we can have substantial skill in the second week. So I'm looking forward to that. It's already happening. Thunderstorms, tornadoes, that's a much harder problem. And that requires, more information. It requires using ensembles at extremely high resolution. And these are areas that we have to work on. So thunderstorms, tornadoes, those are very hard problems. I think we can make progress, but the other type of phenomena, the big storms, I think those we can make very substantial progress in.
Well, what about even longer term predictions? I'm thinking here maybe the Farmer's Almanac that has never hesitated to say next year will be exceptionally dry. You can count on the drought in California to continue. Or if I go to, some medium and they look in their crystal ball, if they only tell me what's going to happen in the next 2 weeks, I probably don't feel like paying them. Does anybody say to you, look, when are you going to be able to tell me what next year's going to be like?
Well, I really can't do that. The Farmer's Almanac has no skill. So I'll throw that out right there. So I wouldn't listen to that. I mean, basically, we have a lot of skill the first week, marginal skill the second week, and our forecast skill fades very substantially after that. Longer term predictions, the only thing we really have that's useful is the connection between the atmosphere and the ocean. And that gives us some skill for things like understanding how El Nino and La Nina correlate with weather months ahead. But other than that, our skill long-term is very, very marginal.
Cliff Mass, thank you so very much for speaking with us.
My pleasure. Thanks.
Cliff Mass is a professor of atmospheric sciences at the University of Washington. Well, up next, why merely the suggestion that the weather could be predicted was laughable less than 2 centuries ago, and what are those weird clouds doing in the Bermuda Triangle?
It's Weather Vane on Big Picture Science. Today, we have sophisticated satellites and computer programs to provide data for weather forecasting, truly astounding technology. And as we've heard, there's a desire to up our game. But all this fancy equipment, it's relatively new.
It wasn't all that long ago when the height of weather forecasting was to look at a rooftop metal rooster to see which way the wind blew, or gaze around for other clues.
People would look at clouds and try and work out the shape of the clouds, if that predicted anything, or the movements of animals, if that was going to give them any indication of what was going to happen.
Writer Peter Moore says that prior to 150 years ago, the phenomena responsible for weather were still a mystery.
I suppose most people just thought it was chaotic. If anything, it was almost a bit like the mood music in a Hitchcock film. I think of it a bit like that, it kind of went one way, then it went another way, and it seemed to be connected sometimes, but then sometimes it didn't with events. So it was a strange, mysterious phenomena.
Then in London, around the 1850s, Admiral Robert Fitzroy, along with a few other daring scientists, shocked the scientific status quo by suggesting that it was possible to produce a weather forecast. This idea created a storm of controversy, says Peter Moore, the author of The Weather Experiment.
The word forecast is a particular word which was coined in the 1860s, and it was coined for this specific reason, which is to divide it from the old ideas of prognostications or prophecies. The word forecast was invented by really the first forecaster, who was called Robert Fitzroy, and he saw these forecasts as a kind of blend of what you could see with your eyes and what you'd know in terms of scientific theory. So it was a blend of the two things. And before that, it had never had the scientific grounding that we would today consider to be part of a forecast. So forecasts are new. 150 years we've been having them. Before that, they came under different names.
But surely, even if they didn't have too much science behind it, they could correlate things like the shapes of clouds with impending storms and stuff like that. I mean, in a way, that's a forecast.
You're right. And it's maybe a facility we've kind of lost a bit nowadays because we're so reliant on the technology to tell us what's going to happen that we don't use our own sense of sight or whatever just to study the clouds or watch what the animals are doing. In the start of the 1800s, this was one of the big embarrassments of science, in a way, that you'd get a bull in a farmer's field that would know it was going to rain before the scientist in his study with all these instruments and thermometers and barometers and things like this. And it's true that the natural world does respond in advance to drops in pressure and things like that. So you've got that on one hand, and then the shapes of clouds is another interesting one. There's lots of old sayings which are attributed to this, but there's one that I remember above all, which is clouds like rocks and towers mean great showers. And you could almost translate that into meteorological parlance of today and say that's a cumulonimbus cloud, rocks and towers up over the atmosphere. And so they kind of come to the same conclusion from a different direction, if you like.
You say that bulls were able to predict the weather, too. I hadn't heard that. What is it that a bull knows that would allow them to predict the weather? Are they bovine barometers or something?
Well, I think that's a nice way of putting it, actually, the bovine barometer. I think there's... this is a very contentious issue. If you go out into the countryside and ask the farmers, they'll tell you that, for example, they will lie down in the field before it rains. That's a very common one. But then you might hear variations that they'll only lie down in this particular part of the field when it's going to rain and so on, So the bovine barometer does exist.
Now, in the 19th century, another accomplishment among the many of the Victorians was indeed to establish weather forecasting as a science. But they were considered rebels, were they not? I mean, and in what sense could they be considered a rebel? After all, weather prediction is something that's beneficial, fairly benign. Nobody gets hurt. Why were they called rebels?
Well, I think it comes down to this issue of prediction within science and applying science before you've established a theory. And there were lots of different theories going on about the atmosphere in the 19th century that were kind of groundbreaking things. So people understanding why the wind would blow in a particular direction or why a storm would move around. But it was very difficult to prove these things because they didn't have the satellites that we have today where you can look down and see everything going. So they had an incomplete theory, or shall we say a contentious theory. And what they were trying to do is really save the lives of sailors at sea who would get caught in these storms. But if you're trying to apply a theory which hasn't the backing of the entire scientific community or isn't established strongly enough, you're going to have dissent. And lots of people just thought that this was beyond the realms of science. And it's only really when you get the telegraph of the 1840s, 1850s, that time, that they start to be able to knit together observations from different places to give us weather maps and pictures of things that happen. And it raised a really interesting question of how much of a prediction is it wise to make, because if you get it wrong, it could have consequences. And the consequences they were worried about was that science would lose its reputation, and that was a big deal for them.
Perhaps you could elaborate a bit on the basic science that needed to be understood. There was Sir Francis Beaufort, Matthew Maury, working out the mystery of the atmosphere's behavior. How did they do that?
Well, there was a few things. First of all, they had to kind of codify the atmosphere in a way that different people could all relate to. So there was things like the Beaufort scale, which was a way of quantifying wind speed, which was a big move forward. There was another innovation from a guy called Luke Howard, who gave different names to clouds. So you have stratus, cumulus and cirrus and so on. So this was a kind of nomenclature which people were able to use. It was really two theorists in the 1830s, one called William Redfield, the other one called James Espy, who really began to understand how hurricanes moved. And this idea that, when we think of a big, tropical cyclone today, you kind of think of this thing spiraling around in the sky. And it's an idea that we have, but they didn't have any of that before. And And it really was the observations of these two men, and it turned into a big scientific argument in the 1830s. But this understanding of storm physics was absolutely vital. So if you're going to be forecasting storms, you need to know how they're going to move, if they're going to move in an anti-clockwise direction and so on. Yeah, that was a real big American achievement, I think.
At the heart of your book is the story of Captain Robert Fitzroy, who wanted to fund a national weather prediction service in England. What was driving him to do this, and what sort of resistance did he meet?
Well, Fitzroy's an absolutely fascinating character. He is best known, really, as Charles Darwin's captain on the Beagle. Fitzroy was a brilliant man, but he had a terrible temper, and he was, I think, what today we'd probably classify as someone who was almost bipolar in his personality. He was very high or he was very low. But he was a very hard worker, and he had these big ideals, and one of his ideals was to decrease the number of fatalities of sailors at sea. Often they'd be caught in storms. And as a sailor himself in the 1850s, he was around members of the British government, and he decided that he wanted to come up with this, kind of idea to issue weather warnings and storm predictions. And so it's really like from this one very strong dynamic personality that we get the Met Office, which is our weather bureau, and that was Fitzroy's idea.
I understand that one of his allies in Parliament was nearly laughed out of the chamber when he suggested that we might be able to someday predict the weather 24 hours in advance.
Yeah, that's absolutely correct. I mean, this was during the vote. They were trying to decide how much money to give the new weather bureau, if you like. And it's a wonderful little exchange, which is documented a bit like a screenplay or something. Today you can read it. And say there's this scientific-minded member of Parliament stands up and says, with the new weather office, we'll soon be able to predict the weather in the metropolis 24 hours before it happens. And then there's like a pause, and on the next line it just says in brackets, laughter. It really sums up how ridiculous an idea it was to these established politicians at the time. But there was obviously a clear need to do something in Fitzroy's opinion, because if you look back at the newspapers from them, it was so often to see accounts of shipwreck or fishermen just disappeared, and this idea that we can just shelter when we know a storm is on its way, they didn't have any of that, so they were very vulnerable, and that's what he was trying to counter.
Well, finally, Peter, when you walk out in the morning on your way to work, assuming you go somewhere else to do your work, do you look up at the clouds and kind of make your own forecast?
Do you know what I do? And I think one of the great thrills that anyone can enjoy is learning to enjoy the skyscape. Over here in Britain, we've got the Cloud Appreciation Society. I'm very proud to say I'm a member of it. And it exists to kind of promote the idea of, relaxing, looking at the sky, appreciating the clouds, and dispelling this concept of blue sky thinking, because the blue skies are much more boring than skies with clouds in, sorry. So I do look at the clouds, and it's always different, and it's always a bit of a show.
Peter Moore, thank you so very much for speaking with us.
Absolute pleasure. Thank you.
Peter Moore is the author of The Weather Experiment, The Pioneers Who Sought to See the Future. Well, Seth, I don't know about you, but I'm tempted to join the Cloud Appreciation Society.
Do you think the Cirrus and the Stratocumulus will appreciate our joining? I have to say that, what Robert Fitzroy was doing here was really classical science. He had observations and he had a theory, and he was sort of trying to combine these two to make a prediction. That's what science is all about. Unfortunately, he was dealing with such a complex, chaotic system, namely the weather, that this was hard. It was much harder than what Newton was trying to do when he was explaining how planets move.
And so hard that, as we heard, he was laughed out of Parliament.
Yeah, well, I can believe that because, the weather changes even over the course of a few miles. How could you possibly know what was going to happen a day down the road, as it were?
Well, despite the enormous refinement of weather forecasting since the 19th century, superstitions about what's really responsible for weather phenomena linger like fog. Consider the Bermuda Triangle.
Yes, this ambiguously defined three-pointed region of the North Atlantic, also known as the Devil's Triangle, is where a supposedly inordinate number of aircraft and ships have disappeared under mysterious circumstances popular culture has floated a few explanations, like paranormal activity, even aliens.
Now, there's no evidence that there's a hex over the Bermuda Triangle, yet the region is susceptible to the formation of hexagonal clouds. The clouds themselves are not that unusual, and they probably shouldn't be taking the rap for swallowing up ships and aircraft, although the audience that recently watched Science Channel's What on Earth might think otherwise.
Meteorologist Stephen Miller got caught in a media Bermuda Triangle of sorts when he and a colleague agreed to be interviewed for a show about Caribbean cloud activity.
The Colorado State University professor knows something about the somewhat striking hexagonal cloud patterns, but he didn't know that his expertise would be used by the TV show to claim that it had identified the mysterious force sinking ships in the Bermuda Triangle.
Steve, when I think of weather, obviously temperature, the wind, and the only visual thing, clouds.
Right.
But even I can see that there are different kinds of clouds. I mean, high thin ones, dark massive ones. What actually determines the shapes of clouds?
Primarily, it's the circulation of the atmosphere itself, the condensation of moisture that results from that circulation. And sometimes you can have updrafts that lift parcels of air into the upper atmosphere and they cool off. Water condenses onto particles and forms clouds. Other times you have just a cooling of the air and the cloud particles can form. So lots of different processes.
Well, so clouds are consequences of the weather, but on the other hand, they're also involved in producing weather, right?
That's correct. We get clouds and they produce weather, and that weather can range from just your garden variety puffy clouds over the afternoon all the way to the most intense supercells that produce tornadoes or hurricanes and so on.
Recently, you were cited in a misleading report as having solved the mystery of the Bermuda Triangle. In a TV show, it was suggested that the Bermuda Triangle shows strange hexagonal-shaped clouds. Now, I've looked at the photos connected with that show, and personally, I found it about as hard to see those hexagons as finding the Virgin Mary in a grilled cheese sandwich. But, of course, you've looked at a lot of clouds. Are there really hexagonal clouds down there?
Well, the interesting thing is, yes, there are, and if you have the right conditions, they look more or less like hexagons, but you do see those all over the world. They have to do with a process where cold air comes over warmer water, and you get a convective response that sets up between the warm lower water and the air moving over it.
You would think that would, maybe it'll make something, vaguely circular or something, but why polygons?
Right. So what's happening is you have sort of these areas of updraft from the instability formed between the warm water and the cooler air. And when you have updrafts all over the place that are somewhat evenly spaced and of equal strength, what ends up happening is the air goes up, it hits against this lid in the lower atmosphere called an inversion, and that air has to go out to the left or right, or horizontally, if you will. And when you have many cells that are next to each other like that, and the air ends up hitting into the other cells that are coming out from the other updrafts, that forces the air back down, and you get a pattern that actually sets up, and you can model this actually and recreate these hexagonal patterns in models. It's kind of interesting. If you just had one updraft, you might just imagine one circular outflow from it. But when you have many right next to each other, they actually interfere with each other. Well, they collide with each other, really, and form these hexagonal patterns.
I kind of wonder whether this has something to do with optimal packing of things. I mean, bees make their honeycomb cells, and they're hexagonal, and some of the bathroom tiles I've seen are hexagonal because you get the most tiles or the most bee cells, if you will, into a given space by making them hexagonal. Anything
Right.
to that?
Maybe the bees can be asked about the Bermuda Triangle then, I'm not sure.
Okay, so what was the suggestion here, that these puffy polygonals were producing local storms somehow? Was that the implication?
Yeah, well, what I was asked to do was try to give an explanation for what I saw in the satellite imagery. And having seen these before all over the world, looking at many different satellites over the years, I said, sure, yeah, I can explain these easily enough, so I did. But what followed was, and what's typically done in these shows is they ask for these teaser remarks, teaser statements to generate interest and intrigue in the story. So they asked me, so what to a layman would be of interest to these clouds? Are they unusual anyway? And so I think my statement was something of the sort that, well, you don't always see these kinds of linear structures, these hexagonal structures in clouds, so it's of interest. I follow that hard upon by my scientific explanation, and the format of the show was always such that there was an expected role for the scientist to debunk and explain things that were presented. In this case, it seems that they took my teaser comment and coupled it with some other comments that really had nothing to do with these particular cloud structures, along with their, exciting graphics and music, to come up with a sensational story.
Yeah, well, create a problem when there wasn't one. So, in fact, even if there is something strange about weather in the Bermuda Triangle, I'm not convinced myself, but even if there is, these clouds have nothing to do with that.
Well, I don't want to jump to any kind of conclusion in terms of weather not being a factor in Bermuda Triangle disappearances. In fact, I think that the explanation of weather phenomena in general as being a plausible explanation for maritime and aircraft aviation disasters is very, very plausible. But, these particular clouds, it's hard to rationalize why they would provide that kind of power that could do that. They're simply very shallow type convective clouds. There's not a lot of strong dynamics associated with them that could give rise to these very high wind speeds, 100-mile-per-hour winds, I think were quoted. Certainly the environment that those clouds reside in, being in the cold air sector of perhaps a powerful storm that's moving through, could be a reason that you could get these sorts of disasters. But the clouds themselves and any effects produced by those clouds, it's very unlikely.
Yeah, well, it sounds like they don't have the muscle to do it.
I was asked about this. There was another person from Arizona State University who was interviewed, and they spliced something together, and it never really got back to anyone to say, hey, does this really make sense? Is this a complete story? Is this conclusion legitimate? And if they had, we could have very easily guided them toward a better conclusion.
Well, this is a region that enjoys a lot of tourism, recreational boating, so maybe the fact that there might be more mishaps of boats and ships happens simply because there are more boats and ships.
I think that's a very reasonable conclusion to deduce.
Steve Miller, thank you so very much for speaking with us.
Thank you.
Stephen Miller is a meteorologist at Colorado State University Cooperative Institute for Research in the Atmosphere.
You know, Molly, I've been thinking a little more about those hexagonal clouds, and I have another analogy. Consider the mushroom cloud from an atomic bomb.
I'd rather not.
Okay, but you know that they're round. If you looked at them from the top, it would look like a mushroom. It's round. But if you had atomic bombs every half mile, in a big grid, they couldn't be round at the top because they would, invade one another's space. And the only pattern that would fit wouldn't be round. It would be hexagonal. So, yeah, hexagonal forms, I think every time you have multiple instances of something, they're probably a good solution.
And is it the updraft of those clouds that is causing weather disturbances?
Well, yes. I mean, not necessarily in the case of bombs, but yeah, the updraft, and then, of course, the air falls back down when it cools. So, you have these vertical motions of air.
So why can't we say that those hexagonal clouds are responsible for the disappearance of the ships and the airplanes?
Well, what Dr. Miller was saying is that, that's conceivable, but he thought it unlikely because he says that these hexagonal clouds didn't have that much energy, not enough to, swallow up a ship.
Well, it's one thing to think that we can predict the weather. It's another to claim that we can control it. And yet humans have done just that. But our limited success in manipulating the weather may be a forecast for our future attempts to control climate.
It's Weather Vane on Big Picture Science. You've heard the old chestnut. Everyone talks about the weather, but no one does anything about it. Well, that's not for lack of trying, however.
We have attempted to deliberately modify the weather, and sometimes with modest success, but we are not able to fully rein in the complex forces of nature, not by a long shot. And yet we continue to try with weather, and with proposals now to try with climate. That is the goal of geoengineering. That is a technological fix to deal with the climate crisis. Sometimes it's called Earth's Plan B.
Alan Robock, a meteorologist and climatologist at the Department of Environmental Sciences at Rutgers University, is a lead author for the Intergovernmental Panel on Climate Change and was a member of that organization when it was awarded the Nobel Peace Prize. As we consider ramping up on global climate control, it might be wise to reflect on our limited success at manipulating local weather.
During World War II, they wanted to get rid of fog at airports so that planes returning from Germany to England could land, and they built troughs along the side of the runway and just burned oil and made huge flames that evaporated the fog and also gave light for them to land. So that was a successful brute force dissipation of fog.
So that actually worked.
Yes.
But
it burned most of the oil that they had in England at the time.
Was that a good use of the oil, I wonder? Well, but how extensive was that? I mean, was it just over maybe a city block or an acre or something like that?
Yes, it was just over the airport at the time when they needed it for the planes to land. It's not a technique that could be used on large scale in any environmental way.
Well, if I'm living, for example, in a state which hasn't had rainfall for a long time, the crops are about to fail, people are complaining, what kind of things could I look to in history that we've tried in the past? I think historian James Fleming has written about this, using massive fires as artificial volcanoes or putting aerosols into the atmosphere. What's been tried?
Yes, Jim Fleming's book, Fixing the Sky, is a wonderful history of this. There have been Indian rain dances, there have been burning fires, but as far as we know, there is no way to do it. The most scientific way that people try now is to put particles into cold clouds that mimic the shape of ice crystals. The idea is that the water in the clouds would evaporate and form ice, and it would grow faster and large enough to fall out and melt and be rain. This type of cloud seeding is being done operationally in different places around the world, but because clouds are so variable, it's really hard to tell what would have happened if they hadn't done it and to prove that they actually have changed the amount of rain.
Well, let me just get this straight, because the reason that it starts to rain, my naive understanding, is that there are little bits of dust in the atmosphere, and the water vapor first condenses on these dust particles, and then they get large enough that they actually fall through the atmosphere and we get them as a rain. It's just trying to imitate that process. Is that what's going on?
Well, the question is, you're right, that's how cloud droplets form, but they're really tiny, and they're kept up by updrafts in the clouds, and they fall, but they don't fall enough to form rain. The question is, how do you get them to grow? Bumping into each other is a very slow process, and so the way most rain forms is that these droplets are below the temperature of freezing. They're called supercooled water droplets. But if there are ice nuclei, not condensation nuclei for water, but ice nuclei that allow ice to form on them, that will allow the ice particles to start to grow, and they grow at the expense of the water droplets, and they grow much faster. So that's the process that produces most rain. The idea of cloud seeding is to enhance the number of ice nuclei, particularly with the chemical silver iodide, which is hexagonally shaped and just about the right size. And that, if you can artificially introduce that into clouds, into supercooled water clouds, then you can get these snowflakes to grow very fast and fall out as rain. That's the idea.
Well, this puts me in mind of things that I remember seeing on television as a kid. They would send aircraft up into the atmosphere, right, and they would spew these, well, I guess it was an iodine compound, into the clouds, and they were telling us how, the era in which you had to worry about no rain and so forth was all going to go away. I believe that this was due to a guy by the name of Irving Crick, who founded the Department of Meteorology at Caltech. But did this thing work? Because at the time, it sure sounded like it was going to work.
Well, first let me tell you about Irving Langmuir, who had a Nobel Prize in physics, and he thought that he knew how to do it, working with Bernard Vonnegut, the brother of Kurt Vonnegut. They found that if they put dry ice, frozen carbon dioxide in, you could definitely freeze out particles and produce snow. But that was very expensive, and so that wasn't done on a large scale. And then they discovered that silver iodide would do it. But they had a lot of hubris. They thought they could really control the weather and produce rain or stop rain. And it turns out oftentimes it didn't work because they didn't know how much to put in. They didn't know which part of the cloud to put in. And sometimes you could reduce rain rather than increase it. If the whole cloud freezes but there's not enough water left to make the snowflakes grow large enough, then it'll just have a cirrus cloud and no rain. Irving Crick tried to sell this process. He would go to farmers and say, look, I'm going to sell you a silver iodide generator, and you put it on your farm. And when a cloud comes over, you turn it on, and the silver iodide will go up into the cloud and cause rain, and it's guaranteed. You only have to pay me if it rains. And he waited till it rained, and they sent him money. It turned out that it didn't make much difference whether they did it or not. And even if it would work downwind, far away from that farm, because they would go up into the air, and by the time it rained, it would rain farther away. He was criticized so much, and the university tried to fire him, and they couldn't because he had tenure, and so they ended up disbanding his department and firing him.
Yeah, I guess he wasn't really the rainmaker that he advertised himself as. Well,
That's
so that
right.
so that really wasn't working. But I can imagine that even aside from farmers who need the rain, governments might need the rain. As you've already pointed out, they might want to manipulate the weather, mightn't they? I mean, did we ever try that during wartime, other than clearing out a runway by burning fires around it?
The United States wanted to cloud seed over the Ho Chi Minh Trail, which was a muddy trail that North Vietnamese would carry the supplies down to South Vietnam during the Vietnam War. They went to India and said, can we test this out in the tropics? And the Indian guys said yes, but there was so much bureaucracy in India, they never got final permission to test it. So they ended up going to Ferdinand Marcos in the Philippines. Can we test it? The next day they were testing it. But what they were testing was the implementation, flying the planes, burning stuff to produce silver iodide. And then they went and did seed clouds over the Ho Chi Minh Trail. I asked a guy from the U.S. Air Force at an American Meteorological Society meeting once, so did it work? And he said, well, none of our spies had rain gauges, so we don't know.
Well, so that doesn't sound like a great experiment.
The CIA also seeded clouds on the way to Cuba to try and make it rain before the clouds got to Cuba to produce a drought and ruin the Cuban sugar harvest. As a result of these, there was a lot of pushing back, and the United Nations produced a treaty called the Environmental Modification Treaty, the convention, and the U.S. signed it and ratified it, and it prevents any government from modifying the environment for hostile purposes. So that's our law now, and the military is forbidden from doing that.
Well, this puts me in mind of what's called HAARP, H-A-A-R-P, High Frequency Active Auroral Research Program. It's a bunch of transmitters, I think, up in the Arctic. And it is claimed, at least in the emails I get, that governments are using this to manipulate the weather to our detriment and to control the population in some sense. Anything to say about HAARP?
Well, I get those emails too. I also study geoengineering, which is an idea to control the climate by producing a cloud in the stratosphere like volcanic eruptions do to reflect sunlight. And people see condensation trails from airplanes, contrails, and they say, oh, the government is spraying, and they call them chemtrails. I'm getting sick when I see them going over. And I try to explain it's just water. I don't know of any government project to put chemicals into the jet fuel. And people believe in this conspiracy and aren't very critical about the information they get. As far as HAARP, it was an ionospheric research program, and they indeed did try to produce a reaction in the ionosphere, but it was on the electrical properties, and it had no effect on weather or climate.
All right, so it seems that we're really not very good at deliberately manipulating the weather, but occasionally we can inadvertently modify the weather, right? I mean, if you live in a city, it's slightly different weather than if you were in the suburbs, or at least the distant suburbs. Can you give me some examples of how we inadvertently modify meteorology?
Well, we talk about the urban heat island. Cities are paved, and so when sunlight hits it, you don't get evaporation, so all the energy goes into heating the ground, and there's a lot of emission of energy by factories and burning fossil fuels and cars and stuff. So cities tend to be warmer than the surrounding area. If we cut down trees and plant crops, we change the land surface, we change the amount of sunlight that's absorbed, we change the amount of evaporation. We also produce particles by burning fossil fuels or digging up or construction, and so these particles can reflect sunlight. They can also affect the properties of water clouds. So inadvertently, there are impacts that humans have on weather. The main inadvertent effect on weather is our burning of fossil fuels, gas, coal, and oil that produces carbon dioxide. The carbon dioxide traps energy and causes global warming. So it's a little hard to distinguish between climate and weather. Climate is just the statistics of weather. It's just a lot of weather. And so our weather is behaving oscillating chaotically in a different envelope, in a warmer envelope, and sea level is higher because of the inadvertent effect of us trying to use energy and turn our lights on and cook our food and drive our cars.
Well, let's talk about climate change then, because you work as a member of the Intergovernmental Panel on Climate Change, the IPCC, and you were doing that when it won the Nobel Prize. You were also a lead author on the most recent report. The IPCC calls for mitigation efforts to address climate change.
Well, that's not correct. The IPCC is not policy prescriptive. IPCC just assesses the science and informs the world governments who asked it to how are humans causing climate change, how will it affect us, and what different policies would do if we implemented them. So if we did mitigation, this is how much climate change we would get, and if we continued business as usual, we would get a lot more climate change. And then it's up to the policymakers to make policy. So IPCC doesn't advocate any policy. It just gives information that lets people know what policies would be effective.
Okay, so maybe I would say that it might precipitate, if I can use that verb, precipitate action, policy changes. One of the things you might consider doing to address climate change would be geoengineering. Let's just engineer our way out of this problem, a technological fix, so to speak. What about that?
So I do a lot of research on that. There's two things that are called geoengineering. One is capturing carbon and taking it out of the atmosphere and burying it. And that's probably a good thing if we could do it cheaply, because that's what's causing the global warming. I don't really work on that. It's very expensive right now. The other idea is to block the sun to counteract the warming from the greenhouse gases and emulate a volcanic eruption. Fly airplanes up into the upper atmosphere with sulfur and continually spray up there to create a permanent cloud that would reflect sunlight. So I do a lot of work on what the risks of that would be as well as the benefits.
Well, I would think that a permanent cloud might, maybe even if it worked, I could imagine if you happen to have your resort home in the area where that cloud was above you all the time, you might not like it. What about putting, orbiting sunshades and just, kind of move the shadow around?
Well, in both cases, the shadow would be for the whole Earth. So you could put, there's an idea of putting satellites out in the Lagrange one point between the sun and Earth. So to block out 1 or 2% of the sunlight, it would just make it hazy all the time, but it would shade the whole Earth. This cloud we're talking about also would basically cover the whole Earth. You put it in the tropics and wind would make it cover the Earth. So it wouldn't matter where your house was. You wouldn't have blue skies anymore. You'd have beautiful sunsets on the other hand. You'd have ozone depletion. You might have a drought because monsoons would be weaker. And I have a list of 26 reasons why it might not be a good idea, why it might be a bad idea. Even if we could do it, whose hand would be on the thermostat? How could we decide what temperature we want the planet to be? Would northern nations want it a little bit warmer, and would islands that are drowning want it colder? And how would we decide? What if people wanted to use it for military purposes once the technology was invented? Or what if there was a big multinational corporation doing it? You want to stop. You can't stop. There's jobs in your congressional district. And so you can imagine a lot of conflict, a lot of ethical things, as well as direct impacts on humans that we might not want to live with. On the other hand, if you could do it, you would reduce global warming and all the negative impacts of that. So which is riskier? That's what we're trying to figure out so that people can make informed policy decisions in the future.
Alan Robock, thank you so very much for speaking with us.
My pleasure.
Alan Robock is a meteorologist and climatologist at the Department of Environmental Sciences at Rutgers University. He is an IPCC lead author and was a member of the organization when it was awarded the Nobel Peace Prize. Thanks to the people who weather any storm to help us produce the show, senior producer Gary Niederhoff and operations manager Barbara Vance.
Thanks also to financial support from Rena Shulsky David and Sammy David, and to the William K. Bose Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life, including scanning the skies with its Allen Telescope Array. And a big thanks also to our listeners.
Your ears have been attuned to the Big Picture Science episode Weather Vane. If you'd like to hear more Big Picture Science episodes, well, you'll find them in our archive at bigpicturescience.org.
And if you're a podcast listener, but you prefer listening to over-the-air radio because you like the static of lightning strikes in your earbuds.
Lightning can't strike in an earbud.
Yeah, well, when it does, it's the last podcast you'll listen to.
And it doesn't do it twice.
Check out the listing on our website of radio stations that carry the program. And if your local station is not on that list, consider letting them know you like the show.
And if you listen to our show via iTunes, we invite you to leave a review on our iTunes page. And to reach us directly with your comments, well, throw in some faint praise and email it all to bigpicturescience@seti.org.
Got your umbrella?